Hi guys, so let's do a quick review of work and energy. So we began our discussion of work in this unit as what happens when a force acts upon an object and causes displacement. We say that that force does work. So when the force is on the axis of motion, we defined work as F times d. But we know that things aren't always that simple, and when a force is acting upon an object at an angle theta with the horizontal, we need to take the component of the force that's on the axis of motion, and that would be F cosine theta. So then our definition of work was F cosine theta times d, where theta is the angle from the horizontal. And when a force is pointing in the direction of motion, we take cosine of 0, which is 1, and when it's pointing opposite to the direction of motion, we take cosine of 180, which is negative 1. And so work in this sense was positive when the force that caused the displacement is in the direction of motion, and work is negative when the force points opposite to the direction of motion, which is different than how we define positive and negative for kinematics and forces. In kinematics and forces, we arbitrarily assigned positive and negative to right and left, and anything that pointed that way respectfully was positive or negative. So then we transitioned our discussion of work into how do we relate it to energy. So we looked at mechanical energy. One type, elastic potential energy or spring energy, is not going to be on the test, but we used it to calculate the solutions to our problem set, and that's calculated as 1/2 kx squared, where x is the distance or displacement that the spring is compressed or stretched, and k is the spring constant. So the main two types of mechanical energy that we focused on was kinetic and gravitational. Kinetic energy is calculated by 1/2 mv squared, and it cannot be negative since the velocity quantity is squared. This is the energy of motion. Gravitational potential energy is calculated as mgh, and this can be negative depending on the zero, but we don't really deal with that in our course quite so much, as this is an algebraic physics course. The work done then by the gravitational force, so when gravity is responsible for a change in height, such as when an object is in free fall or projectile motion, we say that that work done by gravity, W sub g, is equal to mg delta h. So the gravitational force is responsible for that change in height, and that amount of work would also be equal to the change in the energy. Then we had a really brief discussion of conservative and non-conservative forces. So a conservative force is a force that is not dependent on the path, like gravity. And a non-conservative force is a force in which the path of the object matters, like friction or air resistance. Friction or air resistance would act upon this path for the entire distance, whereas gravity, the gravitational force, the conservative force, would only be considered acting on the object for the change in height. And that led us into the work-energy theorem. So we have seen so far energy as an agent of change in the energy of motion, as well as stored energy or potential energy. And we've also seen energy as the mechanism for energy transfer. That you can see in our work equals Fd cosine theta. So combining those two leads us to the idea that there is a constant state of energy within a closed system. So unless there are non-conservative forces acting on the system changing the total energy, then energy is conserved. Now that's not to say that the energy doesn't become transferred into a different type of energy. That can definitely happen within the closed system with no non-conservative forces. And so to calculate that amount, we say the work is equal to delta K plus delta U. The way that we went about solving our problems after the work-energy theorem in conservation of energy was saying that energy here equals energy there, or the total initial kinetic energy plus the total initial potential energy equals the total kinetic final energy plus the total potential final energy. So the big picture idea for solving these problems, I know I saw a lot of you starting with your equations when we did the problem set. But ideally what we would do is we would look at a problem like this. A mass starts with an initial velocity, slides up a ramp, and we are solving for final velocity. And instead of plugging in 1/2 mv squared, etc., I would like you guys to think of the big picture. So in this example, you would say, well, there's KE initial, potential initial is 0, and then there's KE final. And so according to work energy theorem and conservation of energy, the total initial energy has to be equal to the total final energy. And then from there, you can go ahead and plug in your formulas of 1/2 mv squared, mgh, etc. in order to solve for final velocity. But try to get that big picture idea done first. And then it's also great to note that the change in this energy, since the final energy also has potential, so let me go ahead and change that. This change in energy, where initial potential energy went from 0 to some quantity final, is going to be equal to the work done here. Okay, so that's how you'd solve your problems. The last thing that we saw in our packet was this discussion of power. Power, woohoo! So power is the rate of energy change, or it's the work done over time. So we have a formula here, power equals work over time, but work was also equal to F times D, so power also equals FD over time. Recall from kinematics that D over T is velocity, so power equals force times velocity. And that was the last thing that we saw of introduced information in our work and energy unit, so I hope that helps. Have a great weekend.